Okay, so welcome to your mechanical wave notes. First, we need to talk about what is a mechanical wave. Well, any wave is a vibration or a disturbance in space. Okay. Mechanical waves are vibrations or disturbances in space that require a medium through which to travel. Okay, down here at the bottom it says a medium is the substance that all sound waves travel through and need to have in order to move. Now that is true, but more generally we could say that all mechanical waves travel through and need to have in order to move. So a sound wave is just one type of mechanical wave. We could also talk about water waves or waves on a string, but all those things need some medium through which they can travel. Okay, so if I have a vibration or disturbance in space traveling through some medium, that's going to be a mechanical wave. So the anatomy of a wave, some general terms, we'll talk about crests, troughs, amplitudes, wavelengths. We'll also talk about compression and rarefaction, and those are all just different parts of a wave. So we'll talk about these in more detail here in just a second. The first type of wave we'll talk about is called a longitudinal wave. So the wave is moving in one direction, and if that direction is parallel to the direction of the disturbance, that's a longitudinal wave. So you guys made longitudinal waves the other day with your slinky. So you pushed your slinky back and forth in this direction. The wave traveled down the slinky along that direction. Those two things are parallel, and that makes a longitudinal wave. So longitudinal waves will have areas of compression followed by areas of expansion. Compression and expansion. And this word rarefaction here just means, it's just a fancy word for expansion. Now, if we wanted to measure the wavelength of this thing, we need the length of one complete wave. Perhaps we can measure from compression to compression or high expansion to high expansion, as long as we captured one full wave cycle. Sound waves are an important example of a longitudinal wave. Now, the second type of wave is called a transverse wave. So transverse waves, the disturbance is perpendicular to the direction the wave travels. So if this was your slinky or your piece of string or something, if the disturbance was up and down on this page, and then the wave traveled from left to right, that would give us a transverse wave. And transverse waves have this nice sinusoidal shape that you're probably familiar with from math class. The crest of these waves is like the high point of the wave. The trough is the low point of the wave. We have this equilibrium position running down the middle. Okay, that's just kind of like the midline of the wave. And we would measure amplitude from equilibrium to a crest or from equilibrium to a trough, but never both together. If we measure from crest to trough, then we're really measuring double the amplitude. Now, wavelength is the length of one wave. We could catch that by measuring from crest to crest. That would give me the length of a wave. I could also measure from trough to trough. That would give me the length of a wave. Or I can pick any point and then pick a second point as long as that's one full wave cycle. So if I start here, my wave cycle goes up through a crest, back down to equilibrium, back down to a trough, and then back up to equilibrium again. From here to here is the same length as from here to here. Now I've got a picture of a red wave moving across the string over here, and it says, what measurements do you need to make to determine the speed of the red wave? Well, this wave is moving pretty slow, right? So what I could do is I could measure a distance. How far does the wave travel? And then I've got a little timer here. I can measure how long it takes to get there. And then the distance it travels divided by the time would give me the wave speed. Okay, so we could write that like a formula like this, right? So V stands for velocity, and in this case that's my wave speed. This equals delta x over t. Now delta is the Greek letter delta. It's not a triangle, it's actually a Greek letter. And it's an operator that means the change in. And what we're doing here is we're using x as a position. Okay, so I start at some initial position, I move to some final position, and the difference between those two, when I subtract them, tells me the total distance I've moved. We can think about this as being like on a number line, right? Maybe I start off standing at 2 meters, I walk to 5 meters, 5 minus 2 gives me a distance of 3 meters, and that's how far I traveled. So what units would we use for time? We're going to use seconds. For distance, we would use meters. For position, we're also going to use meters. Now, wavelength, or literally the length of a wave, can be found by measuring from crest to crest or trough to trough, or any 2 points, as long as we catch one full wave cycle. Right, so I could choose this point at equilibrium, up through a crest, down through a trough, back to equilibrium. That's a whole wave. So that length right there would be my wavelength. What unit would we use to measure wavelength? Well, wavelength is a length, so we're going to use meters. We use meters to measure wavelength. Now, frequency is how often something happens. So since waves are created by a disturbance, the frequency of a wave is how often the disturbance occurs. So frequency you can think of as the number of disturbances that occur per some unit time. If I have 10 disturbances over a period of time of 5 seconds, 10 divided by 5 will give me a frequency of 2. That means I have 2 disturbances every second. Now, this top quantity, the quantity in the numerator, the number of disturbances, does not actually have a unit, right? You can think of that as kind of being like a counted number. So my units for frequency wind up just being 1 over seconds. Okay, 1 over seconds is the unit for frequency. That has been renamed and is called hertz. So my example I gave before had 10 disturbances in 5 seconds. That has a frequency of 2 hertz, which means 2 disturbances per second. Now, the wave equation is another way that we can look at the speed of a wave, right? So there is a relationship here between wavelength and frequency. And this is the relationship you've been looking at through the Wigler lab. Also, you're going to do the speed of sound lab. But essentially, we're going to look at how are these two things related. Well, let's look at the units for a second. So wavelength is a length, so it's measured in meters. Frequency is measured in hertz, right? But hertz is 1 over seconds. So meters times 1 divided by seconds gives me meters per second. Meters per second is a unit for speed. Let's look at an example here. I have a wave traveling along a rope. It is observed that the oscillator that generates the wave completes 40 vibrations in 30 seconds. Also, a given crest travels 425 centimeters along a rope in 10 seconds. What is the wavelength? Well, let's answer some of these preliminary questions first, right? What is the disturbance causing the wave? Well, the disturbance is coming from the oscillator, right? The oscillator is the thing moving back and forth, right? It's giving me 40 vibrations in 30 seconds. So that's what's causing the disturbance. What is the frequency of that? Well, 40 vibrations in 30 seconds. We'll divide those, right? 40 divided by 30. What quantity is described as being 425 centimeters? Well, 425 centimeters is the distance it travels, right? The crest travels 425 centimeters along a rope. And it does that in 10 seconds. 10 seconds is going to be my time. And then we'll show the equations we need, right? So first we're going to find frequency. So the frequency is 40 vibrations in 30 seconds. That gives me 1.33 hertz. Then I can find the speed of the wave, right? I know it goes a distance of 0.425 meters, right? This 425 centimeters. Oh, I just found a mistake. That's not correct. So 425 centimeters is 4.25 meters. So this decimal is in the wrong place. It should be 4.25. We'll take that and divide that by 10, and that will give me 0.425 meters per second. So this decimal is in the wrong place, but this one's correct. Now we know that's the speed of the wave, right? So that's my v, and I'm looking for the wavelength. I'm looking for lambda. Well, to get lambda by itself, I'm going to divide both sides by frequency. So lambda is the speed of the wave divided by the frequency. And so that gives me a wavelength of 0.0319 meters per second. Okay,